Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in. The traditional gold standard for system reliability, the 5 nines of availability, meaning 99.999% uptime, has long been an aspirational target for critical infrastructure. But the argument now surfacing is that for agentic AI systems, this metric isn't just difficult to achieve, it's fundamentally the wrong target.
It's a provocative claim, certainly. The idea that a system being available could actually be a worse outcome than it being down. For agentic AI, continuous operation isn't necessarily a measure of success if that operation involves incorrect or harmful actions. The system is up, but it's actively failing in a more insidious way.
So it's not just about a server being offline, it's about an AI that's online and perhaps, catastrophically, doing things it shouldn't be. The blast radius of such a failure sounds significantly different from a typical outage.
Precisely. A traditional database going offline causes an interruption of service. An agentic AI making autonomous decisions, especially in a complex, interconnected environment, has the potential for cascading, compounding errors that are far more difficult to detect, halt, or reverse. The damage isn't just a temporary loss of access. It can be persistent, systemic, and even irreversible.
It's important to unpack what agentic AI truly implies here, because it's distinct from, say, a static machine learning model serving recommendations.
Right. Agentic AI refers to systems designed to perceive their environment, form goals, plan a sequence of actions to achieve those goals, and then execute those actions, often without explicit human intervention at each step. It can be thought of as software with a higher degree of autonomy, capable of initiating its own processes, interacting with external APIs, or even deploying code. This is a fundamental shift from a reactive system simply processing inputs to a proactive one generating outputs and affecting state.
So the system isn't waiting for a specific prompt to run a single function, it's constantly observing and deciding what to do next based on its own internal state and goals.
Exactly. And that self-directed, goal-oriented behavior introduces a whole new class of failure modes. With traditional software, you can often trace a failure back to a specific line of code or a misconfiguration. With an agentic system, the failure might originate from a misinterpretation of its goal, an unforeseen interaction between its actions, or an emergent behavior that wasn't explicitly programmed. It's not just bug in the code, it's bug in the intent or execution chain.
This leads directly to the concept of the blast radius. If an agentic AI is making decisions and taking actions, what does a failure look like? Is it simply a calculation error or something more widespread?
It's often far more widespread. Consider an agentic system managing financial portfolios, automating supply chain logistics, or even controlling infrastructure. A misstep isn't just a mistransaction. It could be erroneous trades executed across multiple markets, inventory ordered incorrectly across an entire global network, or critical systems being reconfigured based on flawed reasoning. The blast radius isn't limited to a single component failing. It encompasses all the downstream systems and real-world consequences impacted by the agent's actions. It's a failure not of availability, but of integrity and correctness at scale.
So instead of a server going down for 5 minutes, there could be an agentic system making incorrect decisions for 5 minutes, and those decisions might propagate, leading to millions in losses or critical infrastructure issues. The time frame of the failure might be short, but the consequences are prolonged and expensive to unwind.
Precisely. And this is where the 5 nines metric becomes a relic. 5 nines primarily speaks to uptime. The system is accessible and responding, but an agentic AI can be perfectly up and still be completely out of control, doing exactly the wrong thing, perhaps even exacerbating an issue. It's akin to a self-driving car that's always on and responding to inputs, but reliably driving into a ditch. The system is available, but its behavior is catastrophically unreliable.
It's a shift from measuring whether the lights are on to measuring whether the lights are on and illuminating the correct path.
A good analogy. The traditional approach to reliability engineering has focused heavily on preventing outages, ensuring data integrity, and recovering quickly from known failure modes. Redundant systems are built, failovers are implemented, and designs are made for graceful degradation. But agentic AI introduces an additional layer of complexity: failures of intent and emergent behavior. The system might appear healthy by all traditional monitoring metrics. CPU usage is normal, network latency is fine, requests are being served, yet it's systematically making bad decisions.
And the opacity of these systems, particularly those built on large language models, must compound the challenge. It's not always clear why a decision was made.
Absolutely. The black box nature of many advanced AI models means that while you can observe the inputs and outputs, the internal reasoning process can be incredibly complex and difficult to interpret, even for the system's designers. This makes root cause analysis for agentic failures significantly harder. If an agent takes an unexpected action, pinpointing whether it was due to a faulty perception, a flawed internal model, an incorrect goal interpretation, or an interaction with an external system becomes a Herculean task. Traditional debugging tools are often insufficient for understanding these high-level semantic failures.
This implies a need for a completely different set of observability tools, not just monitoring CPU and memory, but understanding the agent's internal state, its current goals, its planned actions, and ideally, its reasoning behind those actions.
That's the challenge. What's needed is observability into the agent's cognitive process, not just its operational metrics. The ability to audit the chain of thought, the decision points, and the rationale for taking specific actions is crucial. Without this, detecting a subtle drift in behavior that could lead to a large-scale failure becomes incredibly difficult until the blast radius has already expanded considerably. It's a move from monitoring infrastructure health to monitoring behavioral correctness and goal alignment.
So if 5.9s is dead, what are the new reliability paradigms for agentic AI? What replaces it?
The focus shifts dramatically from uptime to safety, correctness, and controllability. This involves several new or re-emphasized approaches. First, robust guardrails are essential, mechanisms that prevent the agent from taking actions outside predefined safe parameters, even if it thinks it's achieving its goal. Second, sophisticated human-in-the-loop strategies, not just for approval, but for continuous monitoring and intervention points. This isn't just about a human clicking yes or no at the end of a process, but being able to pause, redirect, or even roll back complex sequences of actions.
That sounds like a much more active form of human oversight than what is typically seen in automated systems.
It is, and it also implies a need for what some call undo or reversibility mechanisms, not just for data, but for actions. If an agent executes a series of trades or reconfigures a network, there must be a way to quickly identify the erroneous actions and revert their effects, which is far more complex than simply restoring a database backup. It requires careful design of idempotency and transactional integrity across the entire operational scope of the agent.
This also sounds like it has significant implications for system architecture. An agent cannot simply be bolted onto an existing monolithic application.
Exactly. Building agentic systems securely and reliably requires thinking about the boundaries of the agent, its interaction points, and the potential impact of its actions from the ground up. It necessitates modular architectures, clear separation of concerns, and robust APIs with strong access controls. Furthermore, the concept of graceful degradation for an agentic system is not just about reducing features during a load spike. It's about the agent recognizing its limitations, seeking human input, or even pausing its operations when it encounters uncertainty or potential high-stakes scenarios. It's a form of intelligent self-preservation, or at least self-limitation.
So rather than pushing through with potentially wrong actions, a well-designed agentic system should ideally know when to stop and ask for help.
Precisely, and this requires a sophisticated understanding of context, risk assessment, and confidence levels within the agent's architecture itself. It's about building in the equivalent of critical self-reflection and prudence into an automated system. The challenge is immense because it moves beyond purely technical reliability to something approaching ethical and responsible autonomy.
Given all of this, what are the most important takeaways for someone designing or deploying agentic AI systems today?
First, recognize that traditional availability metrics like 5 nines are insufficient and potentially misleading for agentic AI. Your system can be perfectly up while actively causing damage. Second, prioritize safety, correctness, and controllability over sheer operational uptime. This means investing in guardrails, robust human-in-the-loop processes, and mechanisms for reversing actions, not just data.
And the third insight?
The third is to focus on deep observability into the agent's reasoning and intent, not just its infrastructure metrics. Understanding why an agent acts is as critical as knowing that it acted. Without this, mitigating the blast radius becomes a reactive scramble rather than a proactive measure.
This highlights a fundamental shift in how system reliability is approached. How do organizations balance the desire for agentic autonomy with the imperative for safety and control, and what new regulatory or auditing frameworks will inevitably emerge to enforce this balance? That's a wrap on this debug log. Join us next time for more engineering war stories and hard-won lessons. If any of this hit close to home, subscribe and tell your team.
Ship it carefully.